For a moment there, I thought I was going to have to give Jeff's talk, and that was going to be a bit of a disaster. So I'd like to introduce this session on plastics of the future, and I'm going to focus on synthesis, and that's going to lead into Jeff's talk and Karen's talk. But before I begin, I would really like to thank the Welch Foundation. Yesterday was fantastic. The banquet last night was magnificent. And so I'd really like to thank Kathy as well as the board of directors of the Welch Foundation for putting this great ceremony together. As a special treat for Kathy as well, you can also look at my talk as a advertising for the Department of Chemistry at University of Illinois, Urbana-Champaign. You're going to see multiple references to multiple students who have been trained at UIUC. The second thing that I wanted to do was to congratulate Jackie for the Welch Award. We saw last night the voluminous and well-deserved number of awards that Jackie has achieved throughout her career. I'd like to highlight two that often get overlooked, and that is in 2006, Outstanding Director, and also in 2013, Director of the Year Award. This was for her service on the board of Dow Chemical, and Jackie served on the board of Dow Chemical from '93 to 2021. The company changed a lot during those times, but one of the things, if you look at Dow today, they still have this commitment to research. I have about 20 students that are currently at Dow, and they go to Dow because Dow is a company that respects research. And so a special double thanks to Jackie from myself and all of my students for maintaining excellence in research in industry and also talking to people in the corporate world about the importance of research. This is something that we all do, but Jackie does it so much better, obviously. So thank you, Jackie. I'm going to tell you two short stories today about the development of synthetic methods for plastics of the future, and we're going to hear some words over and over again. We're going to hear about discrete materials versus the traditional dispersed materials that we obtain out of polymerizations. And we're also going to hear about functional and sequence-defined monomer units or repeat units in a polymer backbone. They're going to be the features that we're going to concentrate on today. If we look at the first area, and that's accelerated synthesis of polymer libraries, this really goes back to some inspiration from a colleague of Jackie, and that's Dave Terrell, who is currently provost at Caltech. And Dave used to always, many years ago, introduce his talks by saying, if you have a macroscopic polymer object, for example, this lectern here is polymethyl methacrylate. If I look at this as a macroscopic object, there are no two polymer chains in this whole object that are the same. You have dispersity along the backbone, you have different molecular weights, and you have different stereochemistry along the backbone. So for this object, which is so big, not having two molecules the same is kind of an interesting concept. So we then can look at what we would consider to be well-defined polymer chains. And here I'm showing you a low molecular weight polymethyl methacrylate, a MALDI mass spec. And you can see it is a forest of peaks. There's a wide variety of molecular weights, and there's significant chain dispersity in this sample. And that's fine for many physical properties. For making a lectern, where you're concerned just about entanglement molecular weight, that's okay. Ensemble properties are perfect. But if we consider some more advanced applications and opportunities in biomedical systems or nanotechnology, you may want to go away from dispersed polymeric structures to give discrete, functional, as well as sequence-defined materials. And so that's basically the underlying theme that you're going to see throughout my presentation today. And so when we start to think about discrete materials, Jeff Moore was a real pioneer at UC in developing synthetic strategies for making discrete, well-defined oligomers and low molecular weight polymers. As you can see, there's a number of strategies that have been developed by Jeff. The two that I'm showing are accelerated synthesis, where he uses protection, deprotection to build up dimers and tetramers, octamers, etc. This works really well and was one of the first approaches to these well-defined discrete oligomeric materials. Our challenge was that we wanted to do this on a much larger scale. We wanted to get grams and grams of this, but also get it much quicker and much more easily. So we started asking ourselves the question about 5 years ago, is there an easier way to make these discrete materials? Around about the same time, over the last 5 to 10 years, there's been a big development in controlled polymerizations. And so I had two very talented postdocs, Will Gutenkust, who's now down at Georgia Tech, and Jimmy Lawrence, who is down at LSU now. And they came to the realization that using controlled polymerization, we can make really well-defined polymers nowadays, either ring opening polymerization or controlled radical polymerization. We get low dispersity materials in a single step. Can we then take those low dispersity materials and using automated chromatography, those systems becoming widely available, and go to discrete hexamers, heptamers, octamers, etc. And so Will and Jimmy were able to show that this was applicable for a wide variety of systems. And then Jung Fang, who was a graduate student at UIUC in Steve Zimmerman's group, joined my group as a postdoc. And I'm not going to belabor a lot of the underlying synthesis today, but he put a lot of effort into developing the chemistry that you see, where we take commercially available propargyl ethers, terminated with the alkyne unit, living ring opening polymerization then allows him to control the polymerization to give low polydispersity materials. Capping the chain end again with propargyl bromide then gives him a low dispersity material that has polyethers on the backbone and a large number of alkyne units along the backbone. You can see that we can now do this chemistry on large scale, typically 50 to 100 grams, and our dispersity is 1.15, which seems low, but as I'll show you, we still have a lot of different materials inside this one sample. And so we now have a material, it's certainly not discrete, but it has many of the attributes that we want. We can make it on scale, the PEG backbone is biocompatible, and also we have a large number of alkyne units for click functionalization. And so when we run a multi-mass spec of this material, you can see that it is dispersed. We have pentamers and we have high molecular weight materials up to 16 repeat units or higher. But this is where the recent introduction of automated chromatography system comes in very handy, because we can now, on scale, reproducibly take that material and in a single afternoon pass it through a chromatography column to get well-defined tetramer, pentamer, hexamer, so on and so forth. So from that low dispersity material, we now have a library of discrete materials. And just to show you that this is scalable, here I'm showing you the actual structures for the tetramer and the dodecamer, and you can see in the bottom table that Jung Fang started with 12 grams, and he's getting between 0.5 and 1 gram of each of these discrete materials. The 53% is just the pure fractions. We do have some fractions that may be a mixture of hexamer and heptamer And when you add those amounts, the mass recovery is greater than 90%. So this is an efficient way to make these libraries of discrete functional materials. What we can now do is to take advantage of all of the alkyne units that we have along the backbone. And so we can simply do classical click chemistry, in this case introducing the rest of the talk. Okay. Introducing the rest of the talk. So bottom line, we're able to attach these short tetraethylene glycol chains in a quantitative fashion. So we go from a discrete material to another discrete material. Again, I don't want to belabor the point, but Zhongfeng put an enormous amount of effort into adapting this chemistry so that he can do the synthesis and the purification in 96 well plates, because you'll see that we want to make libraries of functional materials, so we need to work in 96 well plates. And so if we just look at this one series that I've been talking about, we can vary the backbone length from n equals 4 to n equals 12, and then because of the click chemistry, we can click on a wide variety of anionic, cationic, or neutral materials. I'm just going to talk about the cationic systems today. We can have guanidinium units and a variety of other cationic systems. And then as a control, I've shown you already the tetraethylene glycol derivative. Again, the chemistry is quantitative, and we can readily do this in 96 well plates. Why would we want to do this? Well, if we have a look at the field of cationic oligomers, they have been well studied to treat multi-resistant bacterial infection, and they do have some challenges. They have much higher toxicities than traditional small molecule antibiotics, and they have poor structure-activity relationships because typically they're examined as dispersed mixtures of materials. So this is a real opportunity for discrete functional oligomers, libraries where we can control the functionality on the backbone as well as the number of functionalities along that backbone. So just going to run through this one short library where we're varying the backbone from 4 to 12. We have a wide variety of side chains, and we're simply going to look at the toxicity of these materials to human cells compared to E. coli. And so you see that there is a big difference as you go across in the number of repeat units, but also what the nature of the backbone is. And if we just zero out the best performers, you can see that for the guanidinium, it really is a sweet spot around about the 6 mer, whereas for the imidinium derivative, we do see much higher performance, but at lower repeat unit numbers. And I would argue that this probably cannot be predicted very easily. And so this is why you need libraries of well-defined materials so that you can see these structure-property relationships. The next question, that was low molecular weight oligomers. Can we push this concept of combining controlled polymerization with automated chromatography to much higher molecular weight polymers? And so this is something that we've done in collaboration with Chris Bates. The motivation is that block copolymers are widely used in many applications, from thermoplastic elastomers to microelectronics. And the performance of those materials is dictated by their nanoscale morphology. Traditionally, we've seen spheres, cylinders, lamella, as I show you on the slide. But are there other morphologies that we just haven't discovered yet? And can we control the size of those morphologies? Especially for microelectronics, lithography is being so precise that being able to control feature sizes of 3.5 to 4 nanometers is actually where the industry is going. So here again, decreasing the dispersity of the polymers may lead to improvements in the morphology. So again, we have students, this time undergraduates, from the University of Illinois. Elizabeth and Steve did their undergraduates at the Department of Chemistry, and they both came to UCSB as graduate students. Demaji is an undergraduate at University of California. And they took on a project that would normally be 2 to 3 PhD theses. Simply, they looked at these diblock copolymers, which are diblock copolymers of dodecyl acrylate, as well as a fluorinated acrylate chain. Molecular weights are now getting truly polymeric, between 5 kilodaltons and 25 kilodaltons, and they do the synthesis using controlled polymerization, and so they get low polydispersities between 1 and 1.25. The idea, and I guess as I said, this would be enough for 2 to 3 theses, is to look at the overall morphology maps when we change the length and the number of fluorinated chains off that second block. And so they learned how to do the synthesis using controlled radical polymerization very well. This is the starting block, the dodecyl acrylate, low dispersity. They then grow out the second perfluorinated block, and you can see again, we get very low dispersity materials, dispersity about 1.1. This is about as good as you can get synthetically. So they made 4 parent materials, different molecular weights, different relative amounts of fluorinated block, and unfortunately, all 4 of those had very poor or no morphologies at all. They were disordered, or they had very, very short range order, which traditionally we would have taken these 4 and said, sorry, we've got to start again. But with the automated chromatography, what they're able to do is to start purifying those well-defined diblock copolymers. So when they put these through the automated chromatography system, they get out fractions, and you can see here that if we just focus on the fluorinated block, we see that the fractions that come out early have very short fluorinated blocks, and then as we elute, the length of the fluorinated block increases. The other nice feature is that if we look at what the parent material was, you see that the extent or the amount of fluorinated block actually straddles that average number really very nicely. If we look at the corresponding dodecyl acrylate block, you can see again, early during the elution, it's almost a homopolymer of polydodecyl acrylate, very short fluorinated block, but as you elute, you actually do have a crossover so that you have less dodecyl acrylate block than the fluorinated block. And again, if we compare that with the average length of the dodecyl block, you can see that we straddle on both sides. So from this one parent material, we get a really wide range of different structures. So one parent material gives us wide range of structures, and instead of having these 4 ill-defined samples, we now have 87 fractionated samples that hopefully you'll appreciate has an unbelievably rich morphology. We now see BCC, we see gyroid, hexagonal, lamella, inverse hexagonal. So from materials that we may have thrown away in the past, we now have the whole of this phase diagram mapped out in 1 to 2 months instead of 3 to 4 years. The other feature that we've been able to see for other samples is that this increased purity and ability to make libraries is actually allowing us to see multiple morphologies that are actually not predicted by theory. They're predicted by theory for metals, but not for polymeric materials. And so, again, hopefully I've shown you that we can take state-of-the-art synthesis, but when we combine it with automated chromatography, we're getting libraries of materials that's allowing us to actually probe important points for applications in nanotechnology. I'm going to simply finish now with the second short story, and that's looking at new degradable polymers. As we have heard throughout today, and Karen and Jeff will also talk about it, recycling and degradation of polymers is difficult. One of the difficult rationales for that is that many of them have a carbon-carbon backbone. And we love that carbon-carbon backbone because it's so stable, but it also impacts degradability and recyclability of these systems. And so Karen, in her talk after Jeff, will be telling us about the use of sustainable building blocks such as a wide variety of sugars to make materials that have properties that mimic commercially available materials from non-sustainable building blocks. And so we took this work as inspiration, that is, using building blocks that you would not traditionally associate with vinyl or polyolefins, but are renewable. And the molecule that we focused on, and this is a collaboration with Javier Reed de Alanez and Chris Bates, is lipoic acid. Now, for many of you that listen to NPR or look at PBS, lipoic acid is commercially available as Nevive. It's a Procter & Gamble product. It's for nerve health. And one of the nice features is that it is cheap. We actually used to buy it from Sigma Aldrich. This is probably the only chemical in my career that I buy from Amazon. We buy it in 1 kilogram bags from Amazon, which is about $50. The same amount from Sigma Aldrich is about $2,000. So, moral of the story, if you can buy your chemicals from Amazon, they're going to be much, much cheaper. And we find the material from Amazon to be much purer than the material from Sigma Aldrich. But this is a